Good evening, everyone, and thanks for tuning in for the first session of the virtual speaker series, Path to Robotics with IEEE RAS, organized by the IEEE Robotics and Automation Society of University of Jaffna. I am your host, 𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏𝗏 In the next few minutes, you will get to know about the IEEE RAS student activities, benefits, opportunities available for IEEE RAS student members, and also on soft robotics, recent research outcomes of Morph Lab, Dyson School of Design Engineering, Imperial College London. If you have any questions on the areas discussed today, please feel free to use the Slido Q&A platform. Selected questions will be answered at the end of the session. Please scan the QR code on screen or click the link found in the chat box and enter the code on screen to join Slido. Now, let me take the pleasure of introducing the keynote speaker of today's session. He obtained his Bachelor in Science in Electrical and Electronic Engineering from the University of Moratuwa, Masters in Electrical Engineering and PhD in System Control and Robotics from Saga University, Japan. Before joining the Dyson School of Design Engineering at Imperial in 2017, he worked at Harvard, MIT, and King's College London. He also set up a bio-inspired robotics lab to support landmine detection work after civil war in Sri Lanka. Currently, he is the director of the Morph Lab and reader in Design Engineering and Robotics, Dyson School of Design Engineering. Would you please welcome Dr. Thrishantha Nanayakkara, Director of Morph Lab, Dyson School of Design Engineering. Sir, over to you.
Thank you, Pramukha, and I'm extremely sorry for the delay in joining this. My Zoom link didn't work due to some reason. So hope you can see my slides. Let me try to share my slides. Can you see my slides?
Yes, sir.
Okay, so I will try to talk about soft robotics and the work I'm doing in my lab. So I'll talk about embodied computation for real-time interaction with natural world. So I think when you talk about robotics, you might wonder why most of the robots we found today cannot do this kind of things, like holding a hamster safely, or getting a robot to examine an abdomen like in a patient, or getting a robot to just go outdoors and then survive. So the after more than kind of 50 years of research across the globe, still we don't have this kind of robots. But if you look at the progression of artificial intelligence without contact, all this deep learning and deep mind and all these things have developed so much that this AI algorithms can even now beat a chess champion or a Go player. So this symbolic AI has developed so much, but people are wondering why physical robots, physical intelligence is not growing that fast. There's something we are missing in our fundamental understanding about interaction with the natural world, physical interaction with the natural world. So I'll try to talk about a few things I think are some missing pieces, and then the work we are doing on that. Right. So the robotics market is growing very fast now. So it's all the predictions made in 2000, let's say 15 for 2017 were had a error margin of about like 34%, and then huge error margins, positive, right? So it's like it had to be like consumer robotics had to be corrected by about 156% positive. So this rapid market growth is fueled by the advancements in basic technologies about AI and physical embodiment and intelligence of robots. So it used to be that, like, all these assembly lines and everything were automated by this kind of hard, rigid robots, like all the motor, the kind of robots, Mitsubishi type of robots, ABB, and all these robots are very rigid, and then you have to have like separated work cells for robots where humans cannot go, right? So they were pretty accurate, repeatable, very efficient, and then very accurate, but like the humans were like kind of segregated from these robots. So these were like 1980s and 1990s, and then things rapidly improved after that, right? With the advent of more collaborative robots. So, right. So, for example, this project we did in 2014 is called the Darwin project. So it is a European Union funded project. So we still work with this kind of rigid robots, but have a little more intelligence to adapt to uncertainty of the environment. For example, if this robot is assembling something and then just picking a piece and then plugging it into another piece, and then what happens if that work cell has uncertainty, right? So somebody, let's say, for example, pushes that away, and then can the robot readapt, and then rather than just repeating a pre-programmed behavior, can it readapt and then rethink about that uncertainty and then adapt, right? And then we went beyond that and then checked if there can be any collaboration between two robots. One robot, let's say if we move that piece further down and then the first robot cannot really reach that, or it is not safe to reach, another buddy robot can come and help that robot. So this kind of collaborative intelligence can come into this kind of work cells, and then this can be extremely useful for workplaces where there's some uncertainty. I mean, it can be agriculture, it can be other disaster response operations and things like that. So it's a departure from typical industrial applications where you have to really have everything in a calibrated environment. But still they were rigid robots. So now what you find in a factory environment is something like this. So more collaborative robots working, like, so this is a universal robot. And then with these robots, you can see humans working around, right? So the human partners and other activity happening in a more open environment. So these robots are called collaborative robots because they are safe, and they have elastic, serial elastic actuators, right? So you can push them and then they can bounce back, and then even they hit them, it is more like somebody hitting you or somebody colliding with you. See, like, you can see these people working around and then just like in a normal live environment. So collaborative robots are picking up very fast, and then most of the work cells are being used or remodified or repurposed for this kind of robots to work. So this person is feeling very safe around them, right? So serial elastic actuators are something like this. Like, so if you have a servo motor like that, and then what it happens is, like, so you have two antagonistic muscles or springs. So you can apply a load to that, and then sorry, a noise in the background. So see this with this kind of serial elastic actuators in the robot. This lady is kind of feeling very safe to work around it, and then they are very safe. right? So these are used in KUKA robots and the most collaborative robots you find today. So this is coming a little closer to soft robots, right? And the soft robotic market is growing roughly at about 40% compound annual growth rate. And then roughly it is now in about $780 million market in 2019, and then it is growing at about 40%. So I mean, different intelligence agencies, market intelligence agencies can vary in their predictions, but soon it is going to be a couple of $1 billion markets. So it is rapidly growing. So at Imperial Robotics Forum has 44 robotics labs. And then we are organized into 3 broad themes like home robotics, health robotics, and infrastructure robotics. And then under each, we have separate teams like domestic, surgery, rehabilitation, environment, vehicles, and social. And some of the labs are like George Malino's lab is working on this kind of soft anchoring in gastrointestinal surgery. Like, so for example, this robot is going inside the body in the gastrointestinal tract, and then when you want to do a surgery, this anchor inflates, and then it kind of latches onto the internal wall of the gastric tract, and then the robot can do surgery. So Ferdinando Biena's lab, and then he is taking inspiration from mosquito needles to do develop surgical instruments to do brain surgery, so that this kind of soft robotic tools can go into the brain, and you can do surgery without damaging healthy tissue. Mirko Koak's lab is taking inspirations from the bees and then developing flying robots. And then YT's lab working on dragonfly-inspired robots and vision. Etienne Burdett's lab, human-robot interaction, and Nicholas Rojas' lab with compliant actuators in grasping, and then my lab is working on mostly soft robotic haptic perception and then embodied intelligence. So I am the present chair of this Imperial Robotics Forum, and then so we have a nice community. Okay. So some of the soft robotic examples. This is an underwater robot. So Wyss Institute at Harvard. So they use that. Most soft robots are inspired by this guy, right? So this octopus. So octopus limbs are very squishy and very soft, but it can solidify or stiffen to do certain tasks, right? So this, if you take inspiration from this kind of soft tentacles of octopus, so you can develop this kind of robots that can grasp very soft things like fungi and things like that, and just sample collection without damaging the environment. And then 𝐒𝐶𝐬𝐿𝐴𝐴𝐻's group is developing this kind of octopus inspired robots for various applications as underwater exploration or surgery and things like that, medical. So this is a collaboration with 𝐒𝐶𝐬𝐿𝐴𝐴𝐻's and Ariana Menciassi group at SSSA, Italy, where I was involved. And then this is where we thought of a surgical robot that can go like an octopus tentacle into the body and then do a surgery, which is naturally safe, and they're safer than sending very hard tools into the body. So this is it is a long way to go before we can do actual surgery, but this is a kind of example.
Tell him that. What is your happy place?
So this kind of robots are also coming up, like like very interactive soft robots with the facial expressions. I will talk more about it later down the line. So continuum robot, I will skip this. So as I said, it is growing at about 40%, and then industry is already using this kind of grasping, soft robotic fingers and universal grippers with granular jamming, and then locomotion robots, and fish robots and rehabilitation robots, and lots of things coming up. So in my lab, we mostly work on this kind of soft robots for soft object grasping. So in this work, Liang He, one of my PhD students who graduated recently, so he developed these fingertips, right? So these fingertips can inflate and wrap around an object to have a stable grasp. And at the same time, these inflated fingertips can work as sensors, right? So when you have an object, and then when you press against this fingertip, the pressure wave can be taken as a sensing signal. So it is both an actuator and a sensor. And then the advantage of this is like the grasping becomes very stable. So for example, like that, and then you can touch and then it can feel it, right? And then you can selectively inflate different parts of the fingertip, and then you can have good perception of the object you are grasping, and then have more form closure around the object. So this kind of grippers, I'm going to little skip things, are useful for industrial applications like soft object grasping in warehouses and things like that. So hold on. So these are like uncertainty tests. So here, so you can see how good the grip is, and then tomatoes and that kind of soft objects, raspberries, strawberries, bananas, that kind of things for mostly vegetable and fruit packing industry. This is useful. We also developed this kind of wearable sensors that for orthosis devices. Like, so the purpose is to have a soft skin underneath the orthosis device, so that we can remotely monitor the patient when the patient goes home, and then if there are pressure points developing under the orthosis device and it's very uncomfortable, the idea is to monitor these pressure points from the hospital, so that the patient doesn't really have to come to the hospital all the time to remorph the orthosis device. The objective is to have remote control ability, so we can send a remote signal to this orthosis device to heat up a certain area where the pressure points is developing, and then just release that pressure. So the important point I want to make here is that with the careful design, you can, let's say, isolate the sensor from external disturbances, right? So if you put a sensor underneath this orthosis device, due to various shear forces, like so the hand is moving around, and then the skin grows and things like that. So that kind of pressures will also be captured if you just leave the sensor. So we wanted to isolate the sensor from that kind of external disturbances. So the way to do that is to have that kind of fish scale type scaling devices around it, and then we optimized the shape so that we have smaller radius scales around the sensor, and then it kind of progressively grows the radii. And if you have that, if you externally apply forces, so those forces the stresses are mostly limited to the outer scales, and it doesn't come to the central sensor area, so the sensor is insulated from that. So the mechanical disturbances don't influence your reading. So this is Xingyang Tan's work. His PhD is about this. This is a collaboration with the Shizhou Central Hospital in China. So this is some interesting work done by MIT. So they are the MIT robotic fish. So these kind of robots are really useful for underwater resource mapping exploration. I think for Sri Lanka, especially in Jaffna, I think the water seabed is shallow, and then there are lots of marine resources to harvest, and then you can do this kind of robots because the tether, so you can have a tether from the robot going to the sea surface, and then it can have the radio transmitters and everything, and or it can have a solar panel to power the robot, and then you can do continuous monitoring of the seabed, and then looking for seaweed, and then even marine for tourism promotion, that kind of thing. So you can easily do this kind of robots. So my real scientific focus is to understand how the embodiment of a soft robot or soft bioinspiration solves very complicated problems, right? So in this octopus, it camouflages into a seaweed within few seconds, right? So can we use this kind of inspirations, right? So like the octopus camouflaging a seaweed, can we use this kind of inspiration to camouflage the internal organ conditions of a patient? Let's say you have a robot in a hospital using this kind of technique, and at home there is a patient who cannot come to the hospital, and then let's say we have a wearable jacket that can scan the internal organ conditions of the patient, and then it can project that scanned data to the hospital, and then the hospital's robot has this kind of a camouflaging thing, and then that physical robot camouflages the patient, so that the doctors can examine the robot, which is now directly mapping the physical conditions of the patient at home, and that can really reduce a lot of congestion in the hospital. So these are the things, some of the things we are thinking of. On the other hand, let's say if you talk about this cheetah, runs very fast, and then it is very difficult for the brain to deal with this kind of rapid dynamics, right? So we suspect that the whole body is also computing other than the brain. So to understand how that kind of things are working is one of the trust areas. So an example I can give is, like, for example, this dead fish. So so on one hand we have the brain and all the controllers, model-based controllers in the brain, but the physical body, like, so the dead fish, the dead fish cannot swim, but if you start a water stream against the body, so it starts to swim, right? So that means the natural shape of the body, and then the stiffness from the head to tail is so tuned that the turbulence in the water can create vortexes and then wobbly movements in the body, so that it has a positive feedback loop to magnify these vortexes to create propulsion forces against the stream, and then the body can swim forward even without a brain. So this passive dynamics in the body and the environment, solving problems on one hand, and then these very model-based, neural network-based controllers on the other hand, and then these things working together is something we suspect to be where the natural intelligence resides, right? So some of the examples I can show you is your own ear. So you have a cochlea, which is a tapered tube of liquid, and then when the time domain pressure waves come and hit it, the eardrum, and then through the this mechanical amplifier, what happens is in the cochlea, because of the tapered shape of the tube, it separates frequency components from low frequency to high frequency. This is like doing a real-time Fourier series, right? And then the brain then picks up these frequency signals, frequency components from 500 hertz, let's say 25 hertz to all the way to 8,000, 20,000 hertz, right? So this cochlear hair pick up these frequency components and inform the brain. So the brain can then cut down the time to do the Fourier series, and then it can directly work on the frequency components which are in the feature space than in the time domain space. And then you can hear very real time, right? So then it is a combination of the brain's effort to do feature recognition and then a physical embodiment computation. They're working together to solve the real-time hearing problem, right? So this Venus trap example is like that. So it is just a bistable structure solving the problem, right? And then this in the goat hoofs, like so these mountain goats, when they climb up those cliffs, it's very difficult to climb those cliffs without slipping. Even if they slip, the brain doesn't have enough time to react because it takes about 100 milliseconds to reach the brain. And then any kind of computation happening in the brain is about 50 milliseconds. And then all the commands have to come down to the muscle fibers, millions of muscle fibers, and amplify them. And all takes about 300 milliseconds, which is not enough to survive on that kind of brain slice. So we suspected that the leg is solving that computational problem without telling the brain. So that is my 𝗏𝗏 𝗏𝗏𝗪𝗀𝗻's PhD in my lab, and she graduated a couple of years ago. So she suspected that the hoof is solving that problem without the brain's involvement. And then she mathematically modeled it and then did very careful experiments. And then she found out that the compliance in the joints help the hoof to amplify vibrations and get the tangential vibrations with tangential slippage to create vibrations that can chop down on the normal surface of slipping, just like a ABS system in a car, right? So when you have ABS, the braking is fast. It works with chopping friction. So this is what she found out. And then she found out that if she have the the optimal ligament stiffness distribution, so she exactly found that, like, so there should be the strong interdigital ligament, and then the fetlock and coffin joint should have compliance. And then she found that it has the maximum slip resistance. So the exciting thing about this is there's no single sensor involved, there's no thinking involved, there's no programs involved or any kind of motors involved. It is just the passive dynamics in the hoof solving a very complex problem of real-time slip reduction. So this is pure embodied intelligence, right? It may be that in the real goat, the brain is slightly involved in conditioning the stiffness of these ligaments, but we are showing that even if there's no brain involvement, it can solve. So you can read these more details in these kind of papers we published. I think I will skip this to limit time. So the other, like I showed you, what the brain can do, what the physical embodiment can do on its own, but I'm a little bit going to talk about how the brain and then the physical embodiment can work together to solve real-time problems. So if you ride a bicycle on a bumpy terrain in a very kind of outdoor environment, what would you do, right? So your brain would ask the body to come off the seat and then ride the bicycle with bent knees, right? So when you ride the bicycle with bent knees, what happens is, so there's an angle dependent damper in the knee joint, and then this damper, the damping coefficient depends on the joint angle of the knee joint. So the brain can select the best damping coefficient by bending the knee a little bit, and then that way it can implement a mechanical low pass filter, so that the knee joint filters out all the noisy components coming from the environment, and then the brain doesn't have to deal with that kind of noise, right? So and then the brain can just focus on low frequency components of just riding the bicycle. So then you can both do, the brain directly involves in the riding the bicycle, and then the brain indirectly conditions the knee joint so that the knee joint can solve the problem of noise rejection. So brain doing two parallel tasks, right? So riding the bicycle and then indirectly conditioning the body to filter out noise. So this is very interesting for us. And then lots of our work, so 𝗏𝗏𝗏𝗏𝗏, her PhD was about that. She found that there is this angle-dependent damper, and then she implemented that kind of angle-dependent damper in a robotic knee joint, and then she found that by doing so, the collision force can be reduced compared to a fixed damper. Not only that, it can reduce the uncertainty of collision forces. So you feel a very uncertain environment, but the brain feels a very kind of filtered environment. So which is very useful for to survive in an uncertain environment. So 𝐏𝐫𝐵𝐻𝐵, he is a Sri Lankan student, and then so he focused on a similar mechanism in the rat whiskers. So he suspected that the rat whiskers are just as good as our eyes because they don't use eyes in the dark burrows, and then their eyes are their whiskers, right? So the curious thing is in the whisker follicle. So this is the follicle where the whisker comes, and the follicle is inside the skin. And then there's a interesting mechanism. So there are two nervous innervations. One is the superficial vibrissalar nerve at the surface epidermis of the skin, and then there's a deep vibrissalar nerve at the bottom of the stem. And then in between there's a ring sulcus. So there's a muscle that can contract and relax. And then he suspected that high frequency components are captured at the superficial vibrissalar nerve, such as the texture information of an object, and then low frequency information such as the geometric information of the object, like the shape of the object, are captured here. And then by contracting and relaxing this ring sulcus, you can kind of rotate this filter to favor high frequency components or low frequency components. For example, if the rat wants to feel the texture of an object, it can contract the muscle and then feel only the texture and not worry too much about the geometry of the object. But if it wants to just ignore the texture but know what shape the object is, then it can relax this muscle and then allow the deep vibrissalar nerve to. So he tested this hypothesis in his PhD using a mechanical follicle where he can control the stiffness of the follicle, just like the ring sulcus of the thing. And then he developed this robot, and then this robot is now, we're trying to use this in the oil and gas industry, where this robot can go inside pipes like a rat, and then scan the surface of the pipes to see the rust situation, and then after cleaning the rust in the pipes, how well this cleaning has been done, how smooth the pipes are, and things like that. And in the construction industry, to go inside with narrow gaps like a rat robot, and then inspect this construction like the structures, is very useful. So given the limited time I have, I think I should so I will just briefly mention about a robot patient we are developing, right? So I'm skipping some of the math about how our fingers are working. I'll go to no, I'm going to skip these things. So we are developing this, a robotic patient which is inspired by that octopus. So the idea is to camouflage the internal organ conditions of a patient in the hospital, and then allow doctors to examine a robotic patient, and then students to also practice examining a robotic patient before going to real patients. So we use soft robotic like organs, so they can be controlled like the liver, and then it can camouflage various physiological conditions, and we can put sensors inside, actuators inside, and then it is very right. So this is our robo patient. I'm going to skip that. So in that robotic organ, we have sensors and actuators that can, create fibrosis conditions, or like swollen liver and intestine. And then this is a calibration experiment we were doing to test our sensing ability. So that is the red is the real force, and the blue is the estimated force from the sensors, and then they're pretty accurate. So in this another project where Thelina and Jacob were working on to express pain from a robotic face, right? So like when you examine the abdomen of a patient, can we show the pain in the robot from various ethnic backgrounds, right? So it's a black male versus a black female, or a white male, white female. The same robot changing from one ethnicity to another, rather than having multiple robots like a white robot versus a black robot. So the same robot can go from like a black female to a white male, white female. So how we do that is to have real-time structural transformations in the face. So we have identified that kind of facial primitives that represent different ethnic groups by taking principal components of many thousands of images from different ethnic and gender groups. And then all what the robot does is like, so if you want to go from a black male to a white female, it does that structural transformation, and then the more detailed information are projected onto the face. And then the idea is to get medical students to examine the robotic patient while the pain is expressed from different ethnic and gender backgrounds. What we find is that the same pain is perceived differently depending on your background and the robotic face background. So the same pain map. So this can only be done in the robotic patient, because we know exactly the mathematical map from the force to the pain level. So we can fix it, and then we can study how people examine different ethnic groups, and then if there are any biases, then we can make very informed technical intervention, so that medical students become very robust and very kind of fair and uniform across various gender and ethnic groups. And then when they go to examine real patients, they can be very robust in their judgments. So that is something we are doing these days. This is an ongoing project. And then so Jacob was an undergraduate student, and then Sibyl is a second year student. She is amazing. So she designed some of these robotic components as a volunteer in my lab. And then Thelina is a Sri Lankan postdoc, and then he's doing more on the scientific side. So these are collaborations with lots of people, right? And then we are studying more gender and ethnicity aspects of robotics, which is very important for training purposes. This is Florence Leong, another PhD student, postdoc in my lab, working on stress analysis of soft tissue interactions. The purpose is to develop a surrogate model of abdominal phantom, and then give a visual feedback to medical students when they examine these things. So These are my collaborators. So Master Gajari is Imperial, and then 𝗏𝗏 is a professor, assistant professor at Imperial in psychology, and Simon Lucian is at the University of Oxford. He's a general practitioner and a teacher in professor in medicine. And Fumi Aida is at Cambridge University, robotics, my collaborator. And then these are the postdocs and the PhD students and undergraduate students. So in this Robotics project, so the whole lab, you can look at everything happening in the Morph Lab in this link. I will stop here to take some questions.
Yes, sir. Thank you, sir. It was a very amazing presentation, and I think this is the first exposure to soft robotics to most of us.
Yeah.
And we have received some questions. So shall I read them to you?
Yeah, sure.
So a student has asked that he wants to know about the hybrid sensor, which uses an actuator approach to soft robotic proprioception using recurrent neural network.
Yeah. So you can use recurrent neural networks to do modeling, but so these days we are using mostly deep learning. I mean, you in deep learning convolutional neural networks, you can have recurrent layers, and you can model, for example, from a force to pain or stress map. So that can be done. We are using them. Yeah.
Thank you, sir. So another student wishes to know the type of simulation softwares that you are using to simulate soft robotics.
Oh, we don't use software. We write our own code in MATLAB, mostly in MATLAB. So it is just analytical. We derive the analytical equations, and we do our own modeling and simulations. But there are soft robotic modeling software, like 𝗏𝗏 project is one, a European Union project. So there are some that kind of things, but like you can use for FEM analysis, we use LS-DYNA, like a ANSYS software. So it's a finite element modeling software. Yeah.
So a student has asked, the artificial muscle as a linear actuator is mimicking natural skeletal muscle behavior. How is this process working?
The artificial muscle, which muscle, which?
He has not specifically mentioned, sir.
If it is the liver phantom, it is we are just using pneumatic actuators. So we just pressurized air to actuate these things. So you can use other techniques like tendons pulled by servo motors, but we use either hydraulic actuators or pneumatic actuators.
Okay, sir. So a student has asked, as a Sri Lankan, what is the best way to start my career if I'm interested to be a part in your lab?
Oh,
Yes.
It is not just my lab. Like, I mean, there are so many robotics labs across the globe. You can really go to any of these exciting labs. So the starting point is, I think, when you're an undergraduate student, really be thorough with your mathematics, right? So it is super important. So what I showed was like just maybe videos, but behind these things are all mathematical modeling. So physical mathematical modeling. So analysis is very important. Being able to model is important. So your mathematical knowledge is very important. And then your software skills, right? So you should be able to program. Either I think Python is great. Knowledge in Python, C++, or MATLAB. So these three are the most frequently used like programming software in the lab, in most labs in robotics. And then the other thing is do projects and then do a small robotics project when you're an undergraduate student, right? So lots of undergraduate students publish these days, right? So when you're maybe, let's say, third year, start a project, focus on a scientific question, and then develop a useful robot. Let's say, I mean, just as I said, like, so you pick some kind of an industry around you. It can be underwater monitoring, or it can be a farm robot, or it can be some robot that is useful in your area, some cottage industry in your area. Develop something and then test a simple scientific question, or it can be just a useful robot like a prosthetic leg or a prosthetic hand for somebody, but publish it, right? So in a local conference or some other conference, publish that. So that gives evidence for people in, professors, that, okay, so you are an undergraduate student who has tried to do a research project. Your mind has a research question, and then you have tested that. No, it is very important in addition to having a first class degree, right? So I mean, first class degree matters, that really is helpful. In addition, a publication and a project that has really gone to that depth is very important. Otherwise, there's so much competition out there to get into a PhD project. That's the biggest advice I can give you. Yeah, so just cut down time on other things you're doing, and then save some time, and then do a project with a supervisor with good advice. Yeah.
Thank you,
Or
sir.
you can make a club, right? So I think 𝗏𝗏 is here. 𝗏𝗏, are you here?
Yes, I'm here. Yes.
Oh, great. So why not we give the space to 𝗏𝗏 so she can give some great advice on software.
Sure, sir.
Yeah.
So thank you, Thrish, for this interesting talk, and thank you for all for like that. So it's very interesting. So maybe because I know some of you may be interested in activities in soft robotics TC, and if you don't know me, I'm Mara Dwini. I'm from the soft robotics TC, and I think first of all, if you would like to join, of course we welcome anyone. For myself, 4 years ago, I was also passionate to be part of the TC. I just I have an idea to do a podcast about soft robotics, and then I proposed that to the TC, and they welcomed that. And now I'm part of it, and also we doing multiple activities. And adding up to the advice by 𝗏𝗏 for undergraduate student, besides publication and doing what you're really passionate about and prove yourself, I think also having the good network. And I think this is a starting point for you all to do that event and talking about that, so that people can have idea what they really want. But for me, what I can suggest based on the expertise that we have in the TC, if you really have an idea, like having a competition, for example, inside university and getting a sponsor from multiple companies to support an event like competition in soft robotics, I think that would be helpful for many students to have a good network, and also for your career, what you really want to do. Do you want to be academia or industry or doing your own thing? So I think that's exposure if you have idea like competition. And currently I'm thinking about if any of you is doing a project about soft robotics and really interesting, we have the podcast about soft. Can you hear me?
Yeah.
Can you hear me?
Yeah, I can hear you.
Yeah. So first of all, you can propose the idea like competition, for example, or creating your own blog or magazine, and that will be later on can be beneficial to people who launch that. So for example, attracting people like companies, and that's something we're already doing. But for the moment, what I can suggest, if you have an interesting idea or project you've done in soft robotics, as I said, we have the Soft Robotics podcast, and now we have audience from more than 80 countries. So it started from scratch, and now it's growing. So I would be happy if any of you have interesting project or wanted to reach your voices. I'm happy to host you in the podcast. That's something we can do. And the other thing also, beyond the ideas, what ideas I can do as a student. For example, we have launched the debates of robotics debate, and we have also Professor Thrishantha in the debate and also in the podcast. So think about what kind of idea do you think could be beneficial for you as a student, and you really want to do it and help you after graduation and having the good network. So if anyone would like to join the TC, please, you can find the website of Robotics TC, or reach to me, I can help in that. So we welcome anyone to join. And if you have any ideas, we can do that and support that and sponsor that as well. So that's something I can help with. And yeah, there's many ideas. You can start a magazine, blog, hosting you on the podcast. And I'm happy to brainstorm or any advice you want. I'm really happy to reach with you all. So let me know what you think.
𝗏𝗏 has been amazing. She's a superstar in soft robotics.
No, thank you.
No, internationally, I mean, she organizes so many events, and then she has been very instrumental in uniting a lot of activities among this global soft robotics community, as a leading member in the IEEE RAS soft robotics technical committee. So 𝗏𝗏 has a lot of authority and resources across the globe to help people. And then if you want to know how to do things and how to start a blog or how to start a magazine, to reach out to the global community, just contact 𝗏𝗏. And I think I shared her email address.
Absolutely, yes. Anyone, I'm happy to talk with anyone. Absolutely.
Yeah. So she organized the first IEEE soft robotics debate, and then she put me on hot plate, like right. I was in that first debate. So it was amazing. So thank you, 𝗏𝗏, for joining today.
Thank you.
Thank you, madam, for joining us. I think we have a question that we can direct it to you. Is it okay, sir?
Yeah, fine. Yeah.
So the students are asking like how being a member in IEEE RAS will benefit, like help them in moving forward in their career of RA in robotics, being a part of a community, like how it will help them.
Yeah, just like so I think starting a blog and then or a magazine, and then connecting that with the IEEE umbrella organization is the way to get visibility across the globe. So 𝗏𝗏 can help with that. So she can get you. You can subscribe to their newsletter, the Soft Robotics newsletter, and then through that you can know all the activities going on in the world, and then the publications. And then in addition, you can publicize your own work through their network, right? So getting to know, like publicizing your work is very important. The student activities in Jaffna, maybe you can give leadership to the rest of Sri Lanka, get people to do competitions, and then you can declare maybe grand challenges that are really relevant to Sri Lanka. So I think that is also important to grab attention. So if you are doing a project that is really unique to Sri Lanka, right? So unique to a Sri Lankan industry, it can be coconut industry, paddy, or fishing or something, then people look at it, right? So if it is very common, then people have seen these kind of things. So do something very unique and like special to Sri Lanka to grab attention from the global community, and then show that you have been original and you have been creative, and then you are grounded, and then people will respect you, and then lots of people will want you in their labs, right? Is that correct, 𝗏𝗏?
Yes, yes, absolutely. I agree with that. That's really perfect advice. I think adding to what Thrish saying, that to find something unique and you really genuine about it, and that's what makes you successful, I believe. So That's
Exactly.
a perfect advice. I agree with that. Absolutely. Yeah.
Yeah. And then, I mean, just giving a, out of a catastrophe in Afghanistan, now the whole world is worried about those few girls who
Yeah.
the robotics team, right? So,
but they are already in US. They already
they
have
are
been
in
there.
US now.
Yes. Someone helped
So,
them to go in the US, and they are now. Yeah.
So see, like, when you do something creative in a very challenging, very difficult environment, the whole world is like, worried about them, and then they get their respect, right?
Yeah, absolutely.
Yes, yes. So then can we go for one last question?
Yeah, sure.
So a student wishes to know about deep learning, how we can relate deep learning for robots, and then working in, and how to train them in 3D workspace.
I mean, deep learning, there's no single solution, right? So we use various deep learning techniques for different applications. For example, for the force to stress map, it's a very complex map, right? So we use GANs, right? So things called generative adversarial networks and infogans. So for that, like information theory GANs, right? So these are little advanced, but like at an undergraduate level, maybe you can study about these things. And then we are also working on pain vocalizations, right? So how to express a pain. So there are like natural NLP, natural language processing, deep networks, and even wave GANs, right? So things called wave GANs. So it can, these generative adversarial networks. I think as an undergraduate student, it is good to learn about the basics of convolutional neural networks and how these GANs work, and then how these things can map, and then take some open data from databases, and then try to train a network. And then you can now easily download in Python. You can use the TensorFlow method. It is like the Keras module is freely available. Use just Keras module to create some deep network and then train something simple, right? So I think that is the way to go. Like, so just use these free resources. TensorFlow is great. Yeah.
Okay, sir. Thank you, sir. Thank you, madam. It was really great to have both of you. And I think most of our participants are interested in also these podcasts that you mentioned about soft robotics. I think I think we can share the details regarding this with them after the session.
Absolutely.
Yeah,
Yes.
Yeah. And then maybe you can organize a challenge and then ask students to develop soft robotic solutions to that challenge, and then do some kind of a exhibition and a demonstration, and then maybe Mava can help you to do a podcast on that, or some kind of video conference or something like that, and then get some publicity for your work. Right.
Yes, sir, sure.
So we'll be super excited to see students from especially developing countries trying out these things to help their communities.
Yes, sir.
Right. Okay.
Thank you, sir. Thank you, madam.
Thank you. All right.
Yes, sir. Now,
yeah. Again, sorry for the delay to join the meeting due to my Zoom problem.
Yes, no, that was fine. Yes, so now I think most of us are inspired by the words, and most of them here are young undergraduates, usually first, second, and third year. So I think surely your words might have inspired them,
Thank you.
them to follow a path in career path in robotics as well. then we shall move to the next event.
My pleasure.
So,
Thank you.
yes.
Thank you very much.
Thank you, sir.
Yeah. Bye-bye.
Now you can find the virtual background for the event in the chat box. Please be prepared for the group photo at the end of the session. Our goal is to create programs that are valuable and relevant and of interest to you. As such, we'll be sending a short survey to you through the chat box, and we would love your feedback. We value your opinion and would appreciate if you could take a few minutes to share your thoughts. Let me now invite the chairperson of IEEE RAS USA, Thrishantha 𝗏𝗏 to deliver the vote of thanks for the session.
Good evening all. This is the very first event organized by IEEE Robotics and Automation Society, University of Jaffna. And as the very first event, we thought of organizing a really marvelous event, and I'm happy to say it has been going through more than we expected. And thank you very much, sir, and for that. So first of all, I would like to convey my heartfelt gratitude for Dr. Nanayakkara for giving you a valuable time in the busy schedule for us to make this event much successful. So for that, I would like to invite you to please accept the token of appreciation we have especially made for you.
All right. Thank you very much.
Thank you, sir. And thank you again for giving such inspirable speech to make our student more understandable in this event. And I'd like to thank our next guest speaker, Ms. 𝗏𝗏𝗿𝗀 for being here with us today. Even though she was here unexpectedly, I would like to give a brief introduction about her. 𝗏𝗏𝗿𝗏𝗏 is an early stage researcher, PhD, working on modeling and simulating self-healing of materials for industrial application as UAV. And she also runs the IEEE Robotics and Automation Society Soft Robotics podcast, and dedicated to the soft robotics community and audience who are interested in soft robotic technology. She interviews guests from both academia and industry to discuss her latest research, besides highlighting the soft robotic challenges in academic and industrial world. Since technology should interact with not only scientists, she also interviews philosophers, kids and lay people about how they feel they think about robotics. And it's always an honor to have you here, madam. And thank you very much being here with us today and sharing your knowledge with us and inviting us to for our students to get involved with the works you are working on. And I would like to thank our student branch advisor, Mr. Thrishantha, and also student branch counselor, Dr. Muthalinga Ramanan, for all the guidance they always give us with being with us. And also I would like to thank Ms. Yalini Balathesan for the valuable support she gave us to make this event much successful. And also I would like to thank Mr. Anuraj for being here with us today. Anuraj for being here with us today, and also all the support he gave us to make this event much successful. Last but not least, I would like to thank all the committee members of Robotics and Automation Society, University of Jaffna, for the hardly commitment they done for up to now and for the future to make this robotic society and make this event more successful. Also, I would like to thank all the participants who were with us today as the active participant to make this event and for your valuable knowledge gathering. So I would like to invite all the participants to be with us and participate on all the upcoming events and start your volunteering career with IEEE Robotics and Automation Society, University of Jaffna. Thank you very much.
Thank you, Thrishantha. It is now time for the group photo. Please turn on your cameras and join for the group photo. Stay tuned for future sessions conducted by IEEE RAS UOJ. Scan the QR code on screen to like, follow, or subscribe us on Facebook, YouTube, LinkedIn, and Twitter. Thank you again. Thank you all for joining us today. Looking forward to see you all at the next session of Path to Robotics with IEEE RAS, and hope you all have a great rest of your day. Thank you.
Thank you. Bye-bye.